equal to 0 AB, and that is equal to 0 MAB. Here the justification is just like this. 0A is the ring element 0. 0 times any ring element is the 0 element itself. Similarly, that is also equal to 0 AB. Here, this 0, this 0, this 0, these are integer 0. But these two zeros are the 0 element in the ring. So that's how we get this result. So, our result means the current one, that one we have already proved, is true for n equal to 0. Assume that the result is true for some non-negative integer n and any m. Keep that in mind, that m will be there in the background, we are not going to mention that specifically. Okay, then now in place of n we are going to put n plus 1. So we have n plus 1a times mb. This is equal to NA plus 1A times MB, which is equal to NA plus A times MB. This is equal to NA MB plus A times MB. That is equal to, let me continue from here. So this is equal to NMAB plus MAB, and this is equal to NM plus M AB, which finally is equal to n plus 1 times M AB. So what are the steps here? It's also somehow like what we have already done. So n plus 1 A in the additive group is this, and that is by definition or by one of the laws of exponent is this, a to the power 1, which is a to the power na. Using our new notation, additive notation, a to the power n is na, and a is of course a, and the operation is additive. So that's how we get this is equal to this. I have written one step in between. So this is equal to this. Then here after that, in this step, I have used the right distributive law. So NAMB plus AMB. Now in writing this equal to this, we have used the induction hypothesis, namely that this result is true for some non-negative integer n and any m. And AMB is equal to MAB. That's what we have proved in the beginning of this solution. Just for this step we needed that, because here m is arbitrary, m is any integer. And after that, this again can be interpreted like this, because NMAB plus MAB is equal to this. So this, by the law of exponent, in this group, this is equal to this. So that's how we are getting this. Okay. So this completes our current induction. So this completes the current induction and proves the result for all non-negative integers in. But there is something else still left to do. Namely, we have to look at the case when n is negative. Okay. Next, let n be negative. Then we have NA, MB. Since n is negative, now the meaning of NA will be this: minus NA. MB. This again by that result, minus A times B is equal to minus of AB. By that we get this. Times MB, minus of this product. Okay. Now here you note that since n is negative, minus n is positive. So what we have proved by induction before this, I can apply that here. And I can write this equal to minus n times m AB. Okay. In this step, I have used this result that we have proved here for non-negative values of n. And this is again equal to, we can simplify a little bit, writing this as minus nm before doing anything more. Okay. So now there are cases, right? Depending on the value of m, whether m is 0 or positive or negative, you can verify that this ultimately becomes equal to nm AB. This I leave to you to see that this is the case. You have three cases: when m is positive, when m is 0, and when m is negative. You have to make sure that this is equal to this. And here our solution ends, because we have now seen all the possibilities. So the result has now been proved in its entirety. So that's how we end the solution to exercise 5. Okay. Now next we look at exercise 6. If D is an integral domain and D is a finite characteristic. Prove that the characteristic of D is a prime number. We have already mentioned about this exercise in the text, that if we have an integral domain of finite characteristic, then its characteristic has to be a prime number. It can never be a composite number. Okay, so let's see the solution to this.